So, the next section of Calculus 2, the next chunk of material, is going to be about sort of completing our knowledge of the calculus of the elementary functions by talking about derivatives and integrals involving the logarithmic, exponential, and inverse trigonometric functions. So far, we have really only looked at the calculus of polynomials and maybe like rational functions. Things that can be built from the power functions and basic arithmetic. And we also know a little bit about the trig functions. But of course, the library of elementary functions includes more than that. And the next chunk of material in Calculus 2 is going to be about, bringing our knowledge up to speed about these additional functions. But before we get started on that, because the next section after this is going to be about logarithmic functions, we're going to start with a review of the fundamental notion of inverse functions. So hopefully this is all a review. I mean, this is all material that you should have seen in an algebra course before. So this section will probably be a review for most of you. But all the same, it sort of sets the stage for the next few sections after this. So first off, let's recall the actual definition of a function. All it is an arbitrary rule that associates elements of one set, called the domain, with elements of another set, called the range, such that every element x of the domain is associated with one and only one element y of the range. So a function is a rule where you take an x from D and then you send it to a y in R. And there is one and only one way to do this. So if a function f has domain D and range R, we write this, f colon D right arrow R. That's just a shorthand notation for a function together with its domain and range. And if a function f associates x with y, then we write f of x is equal to y. So this is just an abstract way of looking at things. Now, given a function with domain D and range R, we ask whether it is possible to find another function which cancels out f. If it exists, such a function is unique, is called the inverse of f, and is denoted by this symbol, this f superscript -1. Now note, when I write it like this, -1 is not an exponent. This is not 1 over f. This is just a symbol. So please don't catch me, don't let me catch you making the mistake of taking f to the -1 and just writing 1 over f. Like that is emphatically not what this is. It's just a symbol. It is not an exponent. Okay, so what do I mean when I say cancel out, though? So an inverse function is a function which cancels this out. So here I am being a little bit more precise about what exactly this means. So if f with domain D and range R is a function, if it exists, the inverse function, denoted f -1, is going to be a function whose domain is the range, and whose range is the domain of the original bit, right? Because it's working in reverse. The idea of the inverse function is that it does exactly the reverse of f. And if it exists, this is the unique function which satisfies the following identities. So if you compose f inverse and f, these two guys cancel each other out, so you just get x back, right? So f inverse and f cancel, so we just get x out. Similarly, if we did it in the other direction, if we composed f and f inverse, again, these guys would cancel out, and you would just have y left over. So that's what I mean when I say cancel out. It means that these two identities have to be satisfied. Another way of writing this is to say that the statement f of x equals y is equivalent to the statement f inverse of y equals x, right? These two sentences are equivalent to each other. So that's another way of defining the inverse, but it's equivalent to saying that these two identities have to be satisfied. So I use the word canceling out, or the phrase canceling out, intentionally here because we're used to canceling things out all the time, right? Like ever since we start learning algebra, we get taught that the way that you solve equations is by, well, canceling out various arithmetic operations until you only have one variable left over, right? Or every time you try to simplify something, you want to cancel everything out. So canceling things out really just means applying inverse functions. So we already know about inverse functions. We've been using them for a while. So for instance, if we have a function whose action is that it adds the number a, then its inverse is the function which subtracts the number a. This is the function which is the exact opposite of this. Subtraction cancels out addition. Similarly, if f is the function which subtracts the number a, then its inverse is the function which adds a. So subtraction and addition are inverse operations to each other. Similarly, if f is the function which multiplies by a number, then its inverse divides by that number, and vice versa. So multiplication and division are inverse operations. And I say let a be non-zero because then we'll have a division by 0, and we don't want to think about that. So yeah, we're already familiar with inverse functions. We use them all the time. At least when it comes to inverses of, arithmetic operations. But of course, the idea of canceling out an operation is much, much deeper than just canceling out arithmetic. Now, some functions do not have inverses. It is not always possible to cancel out the action of a function exactly. So take, for example, the absolute value function. So the absolute value function has as its domain all of the real numbers, so from negative infinity to infinity, all the real numbers, and its range is the collection of positive real numbers, or, well, positive numbers and 0. So that's the absolute value function, the domain and the range. Now notice that the absolute value of 1 is 1, and the absolute value of negative 1 is also 1. Now, suppose for a moment that the absolute value function had an inverse. Call it f inverse. Well, it would follow then, because of this equivalence here, that if f of 1 is equal to 1, then that means that 1 is equal to f inverse of 1. Similarly, if f of negative 1 is 1, then that means negative 1 is f inverse of 1. But wait a second, this is impossible, because we're saying now that f inverse is a function that sends 1 to 1, but it also sends 1 to negative 1. That's impossible. Functions don't do that. By definition, a function takes an input and sends it to only one output. It can't be sending a single input to two separate outputs. So it's impossible. So the absolute value does not have an inverse. So this would suggest to us that functions that do not have inverses are functions that take disparate elements of the domain and map them onto the same element of the range. So the reason the absolute value does not have an inverse is because it takes 1 and negative 1, and it maps both of them onto the same number. So the sort of functions which do have inverses are the functions which don't do this, which don't have this behavior. In other words, the sort of functions which do have inverses take distinct elements of the domain and map them onto distinct elements of the range. So in other words, to put that in symbols and to make the language as precise as possible, a function f with domain d and range r has an inverse with domain r and range d if and only if f maps distinct elements of its domain onto distinct elements of its range. In other words, if x1 and x2 are distinct, they're not the same, then f of x1 and f of x2 must not be the same. So distinct elements get mapped to distinct elements. Now, often when you have a function f and you just have like a formula for it, verifying this property may not be super easy. It's pretty non-trivial, in fact. Thankfully, though, a graphical way of establishing whether this property holds is just to take the horizontal line test. This statement here is equivalent to the statement that the graph of f passes the horizontal line test. So if you draw a horizontal line, it will intersect the graph at most once. So functions like this, functions which pass the horizontal line test, are called one-to-one. And one-to-one functions are guaranteed to have inverses. So as an example, consider the functions given by x to the power n, where n is an odd integer. So these have as their domain all real numbers, and they have as their range all real numbers as well. So if this is odd, then this is in fact a one-to-one function, because if you look at its graph, it clearly passes the horizontal line test. So let me remind you what the graph of these functions, what the graphs of these functions look like. So x to the power 1 looks like that, clearly passes the horizontal line test. X cubed, again, passes the horizontal line test. X to the 5th, x to the 7th, x to the 9th, right? These all pass the horizontal line test. Now, to be fair, it is starting to look like it doesn't pass the horizontal line test. It's starting to look pretty flat down here. But this flatness is an illusion. It is, in fact, very, very, very curvy. I mean, you're going to have to zoom in quite a lot to be able to see the distinction, but actually, I don't think you're ever going to see it. Well, whatever. Point being, you can take my word that they pass the horizontal line test. They just get flatter and flatter towards the origin. So power functions, x to the power of an odd number, those are all one-to-one. And so they have inverses. By contrast, the functions given by x to the power n, where n is even, those are not one-to-one. So again, let me remind you of what those look like. So of course we have x squared, which is a parabola. Well, not one-to-one. It does not pass the horizontal line test. X to the power 4 has the same exact problem. X to the power 6 has the same problem. X to the power 8 has the same problem. And it continues on in this pattern forever. It has the same sort of issue where it appears to get flatter and flatter towards the origin, but aside from that, they all generally look like this. So those functions are not one-to-one, and therefore they don't have inverses. Well, that's a little bit strange, though, because we have the square root, and the square root cancels out the square. So doesn't that mean that the square root is the inverse of x squared? And yet you're telling me here that x squared is not one-to-one, so it doesn't have an inverse. Well, what's going on? So the trick here is that a function is not just its formula. A function is 3 pieces of data. It is the rule for the association, so a formula like x squared, but it is also the domain and the range. A function has 3 pieces of data: the formula, the domain, and the range. So notice that I was very careful to include the domain and the range here. So if the function is x to an even power, where the domain is all real numbers and the range is the non-negative numbers, then indeed it is not one-to-one. However, if we restrict the domain from all numbers to only the positive numbers, then the function that results is 1-to-1. So if we just restrict the domain, right? So, okay, this is clearly not 1-to-1, but if we restrict the domain to be only the non-negative numbers, right? So now the domain is only the non-negative numbers, so we take that entire branch and cut it out. Oh, well, now it is 1-to-1. Now it does pass the horizontal line test. So this function does have an inverse. And the inverse of this function is the square root. That is what the square root is, by definition. So it is a little bit finicky, but it is a technical point that does need to be made. A function is 3 pieces of data: the formula, the domain, and the range. And by changing the domain from all real numbers to only the positive real numbers, we end up getting a function which does have an inverse. And its inverse is the square root. So I just make that point down here. So if n is odd, then the square root function has as its domain and range all the real numbers, because in that case the function's 1-to-1, so there's nothing to worry about. But if n is even, then we do need to chop off the domain a bit. Yeah, we need to chop off half the domain in order to make it 1-to-1. So that is why the domain and range of square roots, fourth roots, sixth roots, and so on do not admit negative numbers, because that is what's required for it to even be defined in the first place. Okay, so just to make sure that we have our definitions understood, if f of 1 is equal to 5, so this is some generic function, we don't know what it is, or we don't have a formula for it. If f of 1 is equal to 5, f of 3 is equal to 7, and f of 8 is equal to -10, find these dudes. Okay, well, this is going to follow straight from the definition. So what is f inverse of 7? Well, let's say for a moment that this is y. Let's just give it a name so that we can work with it. Well, f inverse, by definition, is going to be a function which gets canceled out by f. So if I apply f to both sides, like so, well, f and f inverse have to cancel each other. So we get that 7 has to equal f of y. Well, if a function is 1-to-1, then that means there is one and only one value of the domain which maps onto 7. And well, conveniently enough, we already have that. It's 3. We know that 3 maps onto 7, and because it's 1-to-1, nothing else can possibly map onto 7. Because otherwise it would fail the horizontal line test. So since f is 1-to-1, and f of 3 equals 7, we conclude that y has to equal 7 as well. Oh wait, I'm sorry, 3. Y has to be 3. Yeah. F of 3 equals 7, f of y equals 7, so y has to be 3. Yeah. If there was a different y that mapped onto 7, if, like, for instance, f of -10 mapped onto 7, then that would mean the function is not 1-to-1. And, well, it has to be 1-to-1 because it has an inverse. And, well, we can apply the same logic. We can apply the same logic to the other ones here. So by the same logic, f inverse of 5 is, well, let's see, what gets mapped onto 5? 1. And f inverse of -10, well, what gets mapped onto -10? It's 8. Okay? So, literally just in this equation here, taking the f and moving it to the other side. Like that's literally all that's happening. It's very simple. Okay, so in general, we have the following procedure for constructing inverses. So to find the inverse of a one-to-one function, we write y equals f of x, and then, well, as I just said, to get the inverse, what you do is you take f and move it to the other side, right? Like, if f of x is equal to y, then that means x is equal to f inverse of y. You're taking the function and moving it to the other side. So, in a sense, what we are doing is we are literally just solving this equation for x, right? Like the action of constructing the inverse, the action of taking this symbol and moving it over here, is the action of solving for x, literally. So if this is an equation that we know how to solve, it stands to reason that we know how to find the inverse, because the action of solving it is equivalent to the action of constructing the inverse. So what we're doing is we're leveraging the knowledge of algebra that we already have to construct inverses. And then to express it as a function of x, we just interchange the roles of x and y. Just that way the final equation ends up looking like this. So let us use our knowledge of equation solving to construct an inverse to this dude. So 4x minus 1 over 2x plus 3. So first off, write y equals f of x. Like so. Next, we want to solve this equation for x. So let's see. Well, let's multiply both sides by 2x plus 3. And then let's distribute y on the left-hand side. Like so. Now we want to get x by itself, so let's collect the x terms on the left. And let's put all of the other terms on the right. Okay? So just took the 4x, moved it over here, took the 3y, moved it over here. Now, I can factor out the x on the left. In fact, I can factor out a 2x to get y minus 2 left over. And then finally, to get x by itself, I can divide by 2 and divide by y minus 2. So like so. And finally, so this is just me being pedantic. So I don't like having two negative signs right next to each other like that. So what I'm going to do is I'm going to factor out this negative sign. So here's a little trick that you can do at home if you want. I'm going to factor out this negative sign. Now, having a negative sign on the top of the fraction is the same as having it on the bottom, right? That is morally equivalent, like so. And then, now here's the weird bit. I'm going to take this negative and I'm going to distribute it into the parenthetical expression there on the bottom. So I get 3y plus 1 over 2. So this y becomes a negative y. This negative 2 becomes positive 2. Like so. And that doesn't really give me anything. I just think it looks better. So, yeah. So then finally, to express the inverse as a function of x, we just interchange the roles of x and y. So this becomes y equals, or rather, let's just write it like this. F inverse of x equals 3x plus 1 over 2 minus x. Like so. Okay? So there we go. So constructing inverses is equivalent to solving equations. Those are the same operation. Right. So this last stage here, where we take y and transform it into x, where we're interchanging the roles of x and y, that is suggestive for the graph, because that suggests that the graph of the inverse function can be obtained by taking the graph of the original function and then just switching the coordinates around, right? So instead of so every x coordinate gets turned into a y coordinate, every y coordinate gets turned into an x coordinate. And indeed, this is all you need to do to get the graph of an inverse function. You take the original function, interchange the roles of x and y, and then you get the graph of the inverse. Geometrically, interchanging x and y is the same as performing a reflection about the 45-degree line. So y equals x, that's the 45-degree line going through the origin. So let me just show you an example of what that looks like in GeoGebra. So sketch the graph of this dude and its inverse function using this observation. So let's see. So let's clean this off. So root -1 minus x. Okay. So that's that dude. You can see that it is in fact 1-to-1, so it has an inverse. So to get the inverse, we need to reflect it about the 45-degree line. So y equals x is the 45-degree line. And in GeoGebra, you can do reflections about lines really easily. Here's all you need to do. Just type reflect. And then the object that you want to reflect, which GeoGebra called this dude f, comma, and then the line that you want to reflect it about. So GeoGebra is calling this line g. So reflect the curve f about the line g. And there you go. We got this dude. So this is the graph of the inverse function. So here's the original function, root -1 minus x. Here's the inverse function, whatever that is. And we can come up with a formula for the inverse pretty easily. In fact, let's go ahead and do that. So see lecture video for the picture. I don't want to go through the trouble of exporting the image as a ping and then putting this in here as a... that's what the lecture is for. So see lecture video for the picture. And let's just go ahead and compute the inverse by solving this equation, because now I'm just curious to see what that looks like. So let's see, let's solve this for x. So squaring both sides, we get this. And then if we want to get x by itself, so let's move x over here and move y square over there. Yeah, and then that does it. So there's nothing else to be done but to interchange x and y. Now, I should point something out here. This isn't entirely correct, because this function by itself, -1 minus x squared, that's a parabola. So, right, if we go into GeoGebra and actually type in -1 minus x squared, see, we got the parabola, but that's not correct, right? The actual inverse has to look like this. Whereas the formula that I just came up with is twice of that. So really, the inverse isn't just... So the inverse isn't just given by this formula. It is given by this formula together with the fact that the domain is restricted to the positive numbers. So for x greater than or equal to 0. So this additional restriction is required. And that's sort of that's a subtle point. But, it comes back to the fact that a function isn't just a formula. It's a formula together with a domain, together with a range. And in this case, the true inverse is represented not just by this formula, it's by the formula together with the domain. That x has to be greater than or equal to 0. And you can see that clearly when you look at the sketch, but it's not quite as clear if you were to just work with the formulas. Okay, so up until now, all of this stuff has hopefully been review from algebra. Now let's actually talk about some calculus, though, because a recurring theme in the next few sections is going to be we introduce a function, we introduce its inverse, and then we want to find the derivative of the inverse. So it would be very helpful if we can write the derivative of an inverse function in terms of the derivative of the original function, because that way we could bring to bear all of the knowledge about derivatives that we already have in constructing derivatives of inverses, right? I mean, that means we don't have to go back to the limit definition every single time. We can use the information that we already have. And indeed, there's actually a pretty easy way to do this. So if we write y equals f inverse of x, what we want to do is we want to find y prime, right? We want to find its derivative. So actually, let me just mention that. Oops. So we want to find y prime. We want to differentiate the inverse. Okay, well, by definition, the statement y equals f inverse of x is equivalent to the statement f of y equals x, right? It's as I've been saying. You just take the f and put it on the other side. Yeah, so this is equivalent to the statement f of y equals x. Now, let us differentiate both sides of this equation. Well, on the left, we have to use the chain rule, because y is itself a function of x, right? Y is the inverse function. So from the chain rule, the derivative of this dude is f prime, leave the inside alone, times the derivative of the inside. So it's f prime, leave the inside alone, times whatever the derivative of the inside is. That is literally just the chain rule. On the right, the derivative of x is 1. Okay? Well, we're interested in y prime. So to get y prime by itself, just divide both sides by all of this. So y prime is equal to 1 over f prime at y. So there we go. So that's pretty much the formula for a derivative right there. All we do then to move from here into the boxed statement is to write everything in terms of x. So y prime, so y is the inverse function, so y prime is the derivative of the inverse function, is equal to 1 over f prime at y. And again, since y is f inverse, I'm just taking that and plugging that in. And this is valid as long as you're never dividing by 0, right? That's all that this statement means. It just means that just don't divide by 0. So let us use this formula. So I just want to show you how this formula is used in practice. Let us use this formula to find the derivative of the root functions. Now, we already know that these guys are going to follow the power rule, but, I mean, you've probably never seen it proven before. We've just sort of taken it on faith. So let us actually prove that the derivative of the root functions follow the power rule as we expect them to. So first off, why is this applicable? Well, that's because the root functions are the inverse of, these are inverses of the power functions. So notice that x to the 1 over n is the inverse function of x to the n. And we are going to assume that we know how to differentiate x to the n. That is our premise. So we want to use this knowledge to prove that the same exact thing happens with the roots. And that's just going to be an illustration of this formula up here. So the derivative of the inverse, so using the formula above, the derivative of the inverse, right? The derivative of the inverse is equal to 1 over f prime, so that is the derivative of the original function, so that's n x to the n minus 1, and f prime has to be evaluated at the inverse, right? So we are composing the inverse function in the derivative. So the inverse function is x to the 1 over n. So we are composing the inverse with the derivative of the original thing. And then we can just clean this up a little bit. So this becomes, well, let's see. An exponential phrase raised to an exponent means that you have to multiply the exponents. So actually, I don't need parentheses. So multiplying these guys, we get 1 over n times n minus 1. So that's n minus 1 over n. And we can simplify this a little bit. Yeah, so here's what I'm going to do. Let me write this as, so this is 1 over n times x to the power negative n minus 1 over n, right? Because the negative power just means reciprocals. And then the 1 over n, well, that's a constant, so we can just multiply by that. This is a little bit too big for my taste. Hang on. There we go, that's a little better. And then, well, this is the same on the top here as 1 minus 1 over n, right? So n over n is 1, 1 over n is 1 over n, and then I can take this minus 1 and distribute it. So remember what I'm trying to do here. I'm trying to show that this follows the power rule. So if you distribute this, this negative 1 over n becomes positive, and this positive 1 becomes negative. And hey, wouldn't you know it, that's exactly the power rule. That's exactly the power rule. I took 1 over n, pushed it out front, and then subtracted 1 from it. So the derivatives of root functions follow the power rule, as expected. And that's just a direct application of this formula. So we're going to use this formula a lot in the coming sections to find the derivatives of various inverse functions. Like, for example, we can use this formula to find the derivatives of the inverse trig functions. Because we already know the derivatives of the trig functions, so we just use this formula, and then that's it. That's all you got to do. There might be some hand-wringing involved in, like, simplifying and, getting it down to the point where it looks good and is sufficiently reusable, but the core of the argument is always going to come back down to this formula. So as a final example, just as another application of that formula up there, if f of x is 2x plus cosine x, find the derivative of the inverse specifically at the value 1. So this is sort of a weird question. because it's not asking us to find the derivative of the inverse in general, it's just asking us to find it at this one point. But that's, that's something that this formula will still allow us to do. So by the formula above, this is, well, let's just, right? Whereas x in this case is 1. Now let's see, what are the ingredients here? So there's a couple ingredients we need to fill out. First off, we need to know what f prime is. So we need to know the derivative of this function. So we need to know the derivative. And we also need to know what f inverse of 1 is, right? We need to know f inverse of 1, because once we have this number, we can just plug it into the derivative. We can just plug it into f prime. So those are the ingredients. So f prime is easy enough. The derivative of 2x is 2. The derivative of cosine is minus sine. Oops. Oh. There we go. The derivative of cosine is minus sine. So there's that taken care of. Now, what about f inverse of 1? So this is a little bit trickier, because here's the thing. Well, first off, is this function even 1-to-1? Let's just quickly verify that that is the case. So 2x plus cosine x. Because it's not obvious to me that it is. Let's turn these off. So 2x plus cosine x. Okay, yeah, well, it certainly looks 1-to-1 just from this graph. So there is that. It is 1-to-1, so it does have an inverse. As for what the inverse actually is, though, well, if we wanted to construct the inverse, we would have to solve an equation which, frankly, I don't know how to solve. In fact, I don't even know if it's possible to do so analytically. So if we wanted to construct a formula for the inverse, we would have to solve the equation y equals 2x plus cosine x for x. And I'm not convinced that this is actually possible. Certainly we can do it numerically. We can do it with calculators, but I don't think it's possible to do this by hand. Or it's at least not easy. However, this is overkill, right? For the actual question that we're asking, we don't need to know the whole inverse. We only need to know the value of the inverse at 1. So all we need to do is guess the solution to the following equation. Let's see. Oops. Sorry. So all we need to do is guess the solution to the following equation. So if f inverse at 1 is equal to y, and we want to know what y is, well, by definition, this is the same as saying that 1 is equal to f of y. So this is the same as saying that 1 is equal to, so what's f of y? Well, that's 2y plus cosine y. Now again, we run into the same problem, which is like, I don't know how to solve this, because we would want to solve this for y, But if we can guess the solution to this, then because the function is 1-to-1, that solution is going to be unique. So what are some guesses we can do? Well, if this is a problem that appeared in a book, then you can feel fairly confident that the guesses are going to be... the answer is going to be something that's easily guessable. So let's try, for instance, y equals 0. Let's try y equals 0. That's easy enough. Is that a solution to this equation? Oh, well, indeed it is. Because 2 times 0 is 0. Cosine of 0 is 1. So y equals 0 is the unique solution. And we got that just by guessing. So yeah, so for problems like these where you have to actually guess the value of the inverse, you would try 0, 0, 1, -1. What are some other obvious guesses? Pi, maybe. It's going to be something easy. So what was y again? Well, y was f inverse at 1. That's what we wanted to figure out. So now, plugging this data into the formula, we get... what formula was that? That was this. So f inverse of 1, we have revealed, is 0. F prime was this, 2 minus sine. So that's 2 minus sine at 0. Well, sine at 0 is 0, so this is all just 1/2. And we are done. Yep. So a little bit strange, but again, if you can keep straight in your head like the actual ingredients that are required, it's very straightforward. I mean, you need the derivative, certainly. You need the derivative of what you were given. And then you need the value of the inverse at only one point. And if you need the value of the inverse at only one point, as opposed to infinitely many of them, then usually you can just guess it, which is what we did here. Right. Okay, so that's all that I have to say about this section.